Hi everybody. Can everybody hear me? Am I plugged in? Now am I plugged in? Okay, good. I want to talk about a screening method for rapidly identifying a compact set of non-redundant predictors or indicators that contain independent information. And then with a demonstration application of this technique to something called the extreme Hurst signal. I've asked you to spend some time here with me, so what's in it for you? You get a free copy of the software, which I'll tell you about how to get later. Maybe some new ideas, and if you're interested in this extreme Hurst signal, if you're a Bloomberg user, I can arrange for you to get that too. The agenda motivation for doing this, I'll talk a little bit about the cells method or contingency table approach used to do it. A problem associated with all data mining methods called data mining bias, and a solution to that for getting valid significance testing called the Monte Carlo permutation test. I'll talk a little bit about the uncertainty reduction criterion, which is the measure that we use in the program to judge whether a predictor is useful or not, and then the application to the extreme Hurst signals. The motivation for locating a compact set of predictors is important for both discretionary traders and machine-based traders. Most of you are there any discretionary traders in the room? Okay. It's pretty well known that our feeble brains can deal with 2 or 3 variables at a time, so we've got a limited number of slots, and we have to make sure that we allocate those slots to predictors that are useful and non-redundant. When it comes to trading systems, in theory, you can use an unlimited number of predictors, but in practice, you can't because of something called the curse of dimensionality, that as you introduce a new variable into a predictive model, the model space grows exponentially, the data density drops exponentially, and when you're looking for complex patterns in a high noise environment, you need a certain amount of data density to have any chance of discriminating the real authentic patterns from just noise. The method that we use is a table-based method or a contingency table where the variables are broken up into discrete zones, allowing you to get counts of observations in each zone, like a 2x2 contingency table would be an example of that. And the basic method of discovering an association is using the marginal probability product rule, that if you have 2 independent events, the chance of them both occurring at the same time is the product of their probabilities. And so that gives us an expected cell count if there is no relationship between the indicator and the target, or the combination of indicators, which, by the way, is our null hypothesis, that there is no relationship. And if the count deviates from that significantly, we've got some evidence that we do have a relationship. All of these measures that I'll talk about, chi-square, lambdas, Kramer's V, nothing to do with Kramer on television, and this uncertainty reduction are all based on this principle of looking at the observed count deviation from the expected count. This is the intuition. So let's suppose that our marginal probability product rule gives us an expected cell count like this. Indicator on horizontal axis, targets on the vertical axis, so you've got a standard 2x2 cell structure. And suppose that that is the expected count of X and Y, or indicator and target are not related. If we get a count something like this, there's a big deviation from that expectation. The chi-square goes up, and we can start to see whether we have a significant relationship or not. The nice thing about this method is it generalizes nicely to multiple dimensions. That's supposed to be a 4-dimensional cube up in the corner. But the problem is the curse of dimensionality comes back to bite us again, because as you go up in dimensions, the number of cells goes up exponentially, and the cell counts go down to the point where there's nothing in any of the cells, or in many of the cells not. One of the principles that we've probably all observed in our data is this so-called extreme value principle, that indicators typically have their best information in the tails. And one of the features of this program, NRPS, non-redundant predictor screening, is that it allows you to focus exclusively on the tails. This is the user interface. Non-redundant predictor screening is just one of numerous capabilities in the TSSB software, which you can have a copy of. So we've got the tail focus. Let's see, is there something that, I don't know if this has a, oh, here it is. No, that's not it. Forget it. So you've got tail focus, which is up in that section. I picked up a little thing. I think this thing will. Okay. Then you can split the target variable on its sign, which is important to us sometimes. And then down here, let's see, permutation replications. That I'll talk about in a moment. That's where this Monte Carlo permutation test comes in. The problem is that when you're looking for a best combination of predictors from a much larger candidate set, let's say you've got 100 variables you're looking at, which is not unheard of in our game, and you want to find the best three-dimensional combination, if you were to do that brute force, you'd have over 160,000 combinations. Even if you use a restricted approach, like a stepwise, which most data mining programs will use some variant of that, there's still a large number of combinations. And when you look at a large number of combinations for a best, you wind up with this data mining bias problem. Here we go. So what's the data mining bias problem? Whenever you use a body of data to evaluate many items to find a best according to some criteria, the in-sample performance of that best is upwardly biased. In other words, it's better than it's going to do if you expose it to new data. And as a result of this, applying a traditional significance test fails. You'll wind up rejecting the null hypothesis far more frequently than your alpha value says you should. The reason that data mining bias comes about is that good luck winds up infecting the performance of the winner of the competition. You've looked at many combinations of variables. You wind up picking a best one according to, let's say, chi-square or Cramer's V, or uncertainty reduction, and to a degree, and very possibly to a large degree, it's benefited from just good luck. And that's not going to repeat out of sample. Just to show you an example of how severe this problem is, this table looks at only looking for a single best variable out of maybe about 65. This is the variable name. This is the chi-square. So let's take this variable right here, RSI 62. It gets a chi-square of 10, which would be really a pretty high number. And that gives a conventional p-value. In other words, if you're testing only a single variable, the p-value would be 0.04. So you'd say, whoopee, we've got a significant result. But when we compute a p-value based upon the Monte Carlo permutation method, which takes into account the fact that we've looked through 65 variables to find our best, the p-value is 0.84. An 84% probability that you could have gotten a chi-square of 10.07 by chance alone, even if the indicator has no predictive value. So the conventional significance test, doesn't work. Now, the solution to it, or one solution, is something called the Monte Carlo permutation method, which I talked a little bit about in my first book, Evidence-Based Technical Analysis, and we use a much more advanced form of it in this more recent book. It's a very simple approach. Here's your standard data table. You've got your columns of x's. Then there's your dependent variable, the thing you're trying to predict. And all you do is you randomly scramble the x vector with the target. So in other words, this, instead of these x values being associated with this target value, it might be randomly associated with that one. And you scramble up the data. Now that has the purpose, there's another one. That has the purpose, that random permutation or that random scrambling has the purpose of destroying any predictive relationship that may have existed in the unpermuted data, which, by the way, is our null hypothesis. So we go from original data to permuted data. Now what do we do with the permuted data? We simply apply our machine learning technique, whatever it is, in this case it's non-redundant predictor screening, 100 or 1,000 times to that randomly permuted data, each time re-randomly permuting it, and that gives us a distribution for whatever our test statistic is under the null hypothesis. In other words, the machine learning method is looking for that best. So if it's looking for the best single indicator out of 65, that's what it's doing to produce that distribution. That is the correct distribution for computing a valid p-value. Let's suppose that this is the null distribution on the permuted data resulting from that. We then lay on top of it the test statistic for the method on the actual data, and we get our p-value, and it turns out to be not so good. That would be a valid p-value because the distribution was generated under the condition that there is no predictive information, even when we're looking for a best of. And of course, in machine learning, you're looking through many, many candidate hypotheses on your way to finding your best one. I do want to mention a little bit about uncertainty reduction. How's our time, by the way, Krista? What's that? Okay. Uncertainty reduction is interesting because it's an asymmetric measure of association. Chi-square, Kramer's V, lambda, they're all symmetrical measures. They tell you as much about what the indicator says about the target as the target says about the indicator. We really only care about what the target says about the indicator, and the uncertainty reduction measure does that. Okay, so no need to summarize. You've just heard what I had to say. So I want to talk about the application of this method to something called the extreme Hurst signal, which is a signal that was derived by an outfit called Parallax Investment Research. And I became attracted to it because I was working on a project. We were looking for a variable that would be helpful in shutting off a trend following system, and I thought their signal had some potential for that. So what's the extreme Hurst signal? Its purpose is to predict changes in the directionality regime. And by a regime in directionality, I mean mean reverting, random, or trending. It's based on the Hurst exponent, which quantifies directionality in a time series between 0 and 1, 1 being a perfect trend, 0 being complete mean reversion. When the Hurst exponent is extreme, either close to 0 or close to 1 over many different look-back periods, that is the first component of an extreme Hurst signal. And it has, the implication is obvious, if it works, is that it advises a trend following system user when to shut off their system, and a mean reversion system user when to shut off their system or re-engage it. The Hurst exponent is related to something called the fractal dimension. And the fractal dimension, unlike the Euclidean dimensions we studied in high school, like a line of 1 dimension, a plane having 2, a cube having 3, a fractal dimension can have any real numbered value, like 1.23 or 2.53, whatever. Fractal dimensions are a development of a mathematician named Mandelbrot, who was an IBM fellow, and he felt that this was a useful concept for describing real-world objects. Objects that are rough, that have holes in them, that are not smooth. To give you a sense of it, a flat sheet of paper, at least on its surface, is 2 dimensions. A sphere has 3. But if you take a piece of paper and crumble it up into a ball, it's neither a sphere, but it's not a flat piece of paper. It has a fractal dimension of somewhere between 2 and 3. We're more interested in the domain between 1 and 2 as time series analysts. Straight line has 1, a plane has 2, but if we take a line and sort of crumple it up, it doesn't quite fill up a plane completely, but it does partially, so it has a fractal dimension of some number between 1 and 3. The Hurst exponent is nothing more than 2 minus the fractal dimension, so it's just a remapped version of the fractal dimension. The Hurst exponent lies between 1 and 0. So we can use the Hurst exponent to characterize the directionality of a time series, from mean reverting down close to 0 to random at 50. By the way, the random at 50 is very much related to the variance ratio test that you may be familiar with, that was written about by Andy Lowe and his co-author, I forget who it was, Minsky or McKinley or something like that. McKinley, I think. And then when you get a Hurst exponent up near 1, you have highly directional trends either up or down. Trend following systems do well here, mean reversion systems do well there, and in the middle, nothing does very well. So mean reverting and trending markets have, at least historically, degrees of predictability. But that's not what the extreme Hurst signal is about. The extreme Hurst signal is about predicting when a prior regime of directionality, like mean reverting, is going to change to something like trending. Now, here are some time series with different Hurst exponents. The one at 0.9, you could imagine laying a moving average over that and probably doing pretty well. And at 0.1, doing quite nicely with a mean reverting system. There is a property that fractal objects have called scale invariance, which simply means that the fractal dimension, or Hurst exponent, is the same no matter how you look at it, no matter how you magnify it. So this is an example of an artificial fractal. It has a certain Hurst exponent or fractal dimension. But if you look at it at different magnifications, it's going to still have the same Hurst exponent. It turns out that financial market time series don't display this property except infrequently. And that's what parallax means by discrete scale invariance. At discrete times, financial time series do show scale invariance. And that means that the Hurst exponent computed at various look-back levels is going to take on roughly similar values. So they asked the question, what happens when scale invariance shows up in a financial market time series and that value is either close to 0 or close to 1? And that was the basis of this extreme Hurst signal. So the purpose is to predict a change in the directionality regime, that when many of the Hurst exponents on many time scales are close to the same number, their contention is that that regime of directionality has gotten old, long in the tooth, and it's about to die and give way to something new. So it may be a signal to systems traders to change their strategy. One of the other features of the extreme Hurst signal, beyond this discrete scale invariance, is something called log periodicity. And any of you who are familiar with the writings of Dieter Sornet are familiar with this idea. Log periodicity is unlike simple periodic oscillations where the peaks and valleys have similar wavelengths between peaks and troughs. In log periodic motion, the period changes from cycle to cycle by a constant factor. And this is displayed in certain physical systems before they break down, like before a bridge starts to vibrate itself into destruction. What the parallax people found is that as you approach the time of an extreme Hurst signal, the log periodic motion is compressive, and after the signal, it expands. There are 3 types of extreme Hurst signals: a top extension, a bottom extension, and a compression. In a top extension, you've had a period of extreme uptrending motion, and then you get this signal, and then that's predicting that the uptrend is over. Here's an example. I don't know if you can see that slide, but just before the 1929 crash, there was a sequence on the monthly bar chart of these top extension signals. So there was a top extension signal in the yen in 1995. There was a sequence of top extension signals prior to the 1987 crash, although some of them came more than a year before the crash. There was one right before the market peaked out in 2007, and one occurred just at the end of May. There was also a bottom extension signal in October 2008. The bottom extension is the second type of extreme Hurst signal, and it comes after a period of extreme downtrending behavior. And lastly is the compression signal, which comes at the end of a period of extreme mean reversion. And that means that a new trend is likely to emerge. Okay, but, and here are some examples of that. Obviously, not all of these signals work out. How are we doing time-wise? Okay, not all of these signals work out. Here are some premature signals. So part of this extreme Hurst signal is a filtering mechanism that tries to get rid of some of those. And that's where the interaction between Parallax and Hood River research started. They came to us and said, could we use our data mining methods to look at a set of variables that they came up with that they thought had information for getting rid of some of these bad signals. So that's what we did. We ran our non-redundant predictor screening against their 32 different variables and came up with some low-dimensional filters for their signals. I'm going to show you a sequence of pictures that look like this. They're predictive heat maps. On the vertical axis is one variable or indicator. On the horizontal axis is another. And the color represents the value of the dependent or target variable, which is future looking. Since we're looking at bottom extension signals, what we're looking for is when there are high values of the target variable, which are represented in green. So in this region here, on this particular two-dimensional map, that's where you get your best extreme Hurst signals, bottom extension signals. So min HEP, whatever that is, and H area, whatever that is, were identified by this non-redundant predictor screen as being useful and non-redundant. Here's another one of these heat maps, H len and H area. And again, you see a region dominated by strong upside reversals indicated by the green color. It's also, one of the things I should point out is because non-redundant predictor screening doesn't assume the nature of the relationship, it can discover these sort of these nonlinear patterns. Here's another one. It's called min HEP and H len, and you get the best signals up in the corner. But these are just two-dimensional plots. So what happens if you look at a third dimension? You can't see that very easily here. So what I did is min HEP and H len, and then introduced a third variable, and then looked at that space at various slices throughout the space. Slices along a variable called Zn. Again, I don't know what these things are. So what we did was we took the plot I just showed you, min HEP versus H len. This is the two-dimensional plot. And then we start looking at what the pattern looks like as we move along Zn from its 99th percentile onto its first percentile, and this is what you see. I don't know how clearly these are showing up, but so you can see as you move along that third axis, the pattern changes a bit. And here we are at the first percentile of Zn. Okay, that's it. The software you can have by going to tssbsoftware.com and download it. There is also a 200-page user documentation. And if you're interested in the extreme Hurst signal, give me your business card. I'll forward it on to Parallax, and they'll hook you up either on Bloomberg, where it's available, or on TradeStation, if you have TradeStation. I also want to mention this book that Dr. Tim Masters and I recently came out with, Statistically Sound Machine Learning for the Algorithmic Trading of Financial Instruments. It's about the software. You don't need the book if you're just going to use non-redundant predictor screening, because that's just one easy-to-use element in the program. But if you really want to take advantage of this software, and it has committees and ensembles, a new type of committee called oracles, 10 different kinds of machine learning things. It's got a lot of stuff in there, complete indicator library, no programming needed. Then you want to get this book. But modesty and humility prevent me from extolling the virtues of this book. But if I weren't one of the authors, I'd say go out and get it. And that's all I've got. If there are any questions, I'll take some questions. Ram?
David, nice job. I had a question around, my question was around, I like how you took the third dimension and you evaluated the relationship between the first two variables as you move along the third dimension. Have you considered doing that along the time series dimension?
That could be done. We don't have the capability at the moment. In other words, a two-dimensional plot, let's say for a 5-year segment, and then moving that window through time to see if it's time stable. Very interesting idea. We have not done that yet.
Okay, let me know when you do.
Well, anybody who wants to make a contribution to our effort, there's a button on TSSB website software, make a PayPal contribution, and those things go towards the creation of a better and better piece of software.